Hi, my name is Michaela Munson, and I will be modeling the atmospheric dispersion of vinyl chloride in the East Palestine Train Derailment. As many of you remember, in 2023, a train in Ohio derailed, releasing 1.1 million pounds of vinyl chloride, which is highly toxic and volatile, which led to the evacuation of 5,000 people. Vinyl chloride can persist in the environment, and long-term exposure to it is related to cancer, lung disease, and even death. For this project, we will be considering the acute exposure limit of 1.3 milligrams per meter cubed set by the APA, and at these levels, it can cause dizziness, fainting, and eye and respiratory irritation. The objective is to model the vinyl chloride concentration at ground level, so we want to know what the concentration was within 100 feet of the source and within the 1 mile evacuation radius. From there, we want to determine if people at the evacuation radius were exposed to unhealthy levels of vinyl chloride and at what radius were they within the limit. This plume will be modeled with a point source continuous release. We know that it's a point source because it spreads in the X, Y, and Z directions. Vinyl chloride does decay in the atmosphere, but no other reactions are considered. A Peclet number of 478 was calculated, which is much greater than 1, so that tells us that it's evection dominated. Similarly, there was a controlled release of vinyl chloride for 3 hours, and we have an arrival time at the radius at 2 minutes. So because our release time is much greater than our arrival, we know it's a continuous release. Here we have our PDE governing equation and boundary conditions. Our PDE is at steady state, since the change in concentration with respect to time is 0. Our Peclet number tells us that it's evection dominated. There is a first order decay of vinyl chloride with a half-life of 3.2 days. We have no sources or sinks, and there is an impermeable boundary at the ground, meaning the net flux in Z is 0 at the boundary. Similarly, the concentration as it goes in the X and Y direction approaches 0. We'll be using our model to solve for concentration at human height, at the evacuation radius, and within 100 feet of the source, and then we'll determine if that concentration surpasses the acute screening value of 1.3 milligrams per meter cubed set by the EPA. Our solution is a function of the mass flow rate of vinyl chloride, the dispersion coefficients, the position that we're looking at, the velocity in x, and our decay rate. Because the ground is impermeable, we will be adding an image source starting at -z. Some of the variables I was able to find was the wind speed and direction, which was going 12 meters per second in the x direction, the half-life of vinyl chloride, which was 3.2 days, the acute exposure limit, which is 1.3 milligrams per meter cubed, and the mass released, which is 453,000 kilograms, or 1.1 million pounds, in the release time of 3 hours. For calculating the concentration at the evacuation radius, I calculated the dispersion coefficients in Y and Z using the Martin's model. For the dispersion in Y, I calculated 40.5 meters squared per second, and for the dispersion in Z, I calculated 7.2 meters squared per second. The Z that we'll be solving for is 1.5 meters above the ground, which is a little less than the average human height. For X, we will be looking at the evacuation radius of 1 mile or 1,600 meters downwind from the fire. For solving for the concentration 100 feet from the source, we have a dispersion coefficient in Y of 1.77 meters squared per second and a dispersion coefficient in Z of 0.17 meters squared per second. We will once again be looking at the Z at a little less than human height, or 1.5 meters, and we'll be looking at 100 feet or 30.5 meters away from the source. The unknown that we're solving for here is concentration, but there were some other things that we had to go ahead and solve for. We had to solve for m dot using our total mass released, and we had to solve for our k value using the half-life. So when I plugged all the knowns into our advection dispersion solution in Python, these were our visualizations. The ones on the top show the plume in X and Y directions, and the one on the bottom shows the plume in X and Z dimensions. And the color scale visualizes the concentration in milligrams per meter cubed. And the red dot represents the area of interest. The graph on the left shows the concentration 100 feet away from the source, which is 1.6 times 10 to the 5th milligrams per meter cubed, which is way over the 1.3 milligrams per meter cubed limit, making it very, very unhealthy to be around. The center graph shows the concentration at the evacuation zone of 1 mile, which was 0 milligrams per meter cubed, making it very safe for people at that limit. And on the right shows a graph that I made just for fun to show at what radius the concentration begins to be an acceptable concentration for acute exposure. So at 0.4 miles away from the fire, it begins to meet that health limit set by the EPA. So these graphs show that the evacuation radius of 1 mile was completely appropriate and those people were safe in that area. My model of the East Palestine train derailment was by no means perfect, and there were a lot of simplifications in this. One of these big simplifications is that the ground is not necessarily an impermeable boundary, but nor is it a perfectly sorbent boundary. We do know that there is an interaction between vinyl chloride and the water and soil, but more research would have to be done to figure out how these do interact with each other. Another simplification is that I only considered the decay of vinyl chloride in just plain air in a laboratory, and I did not consider how it would interact with other chemicals or the heat from the fire. Lastly, there was a lot of variation in the velocity and direction of the wind that day, which would affect our dispersion coefficients. So the East Palestine Plume was actually already modeled by IMAC, which is the Interagency Modeling Atmospheric Assessment Center. So the way that they did this is they collected actual concentration data from the plume, and in their model they accounted for settling that is dependent on the particle size, variations in wind speed and direction, and accounted for an inversion layer in the atmosphere. So if I had more time to refine my model, I would use actual collected concentration data and use some of the factors that IMAC did account for. So when IMAC and the EPA collected data for their model, they used two main methods. The first was ASPECT, or Airborne Spectral Photometric Environmental Collection Technology, and basically this is a plane that collects chemical data with sensors on it, such as infrared cameras, a spectrometer, and it marks all that information with coordinates. The other thing that they did use was ground methods of measurements. So on the right here, you can see a little canister. This lets air in on a given amount of time, and that collects VOCs. Then that's brought back to a lab to measure how many VOCs collected in that canister for that time. So while doing research, I found that scientists and engineers use a whole bunch of different programs and packages to model atmospheric plumes. The one that I would probably use if I were going to model this again is called AirMod, and that is a steady state plume model, and that accounts for dispersion based on boundary layer turbulence, scaling, and the surface of for surface sources and elevated sources and variable terrain. So one of the inputs you have to put into that is a digital elevation model. So once again, if I had more time, I would think more about what is actually happening to vinyl chloride when it meets the ground, if it's sorbing, if it's impermeable, or somewhere in between. I would also take more into account how it could be interacting with other things in the atmosphere and, looking more into the decay. I would collect hopefully real-time data or find that online somewhere and then put that into a program such as AirMod. Here are my sources, and I hope that this was fun and informative to watch. Thank you.